Hear an echo? I think we're good? All right.
Don't hear an echo? Okay.
Great.
All right.
No problem. Okay, so as Joe said, my name is Gialluca. I'm a PhD candidate at the University of Washington in Seattle. Today I'm going to be telling you about two different research projects that I've been involved with. Both are into supporting current and future missions. Specifically, the first one I'll talk to you about is on work for interpreting the atmospheres of the TRAPPIST-1 planets with JWST. And the second is preparing for HWO, and in particular, considering the stray light constraints that may be affecting HWO as we start the mission design process. So to start, let's talk about this TRAPPIST work, and I just want to contextualize the problem. M-dwarf habitable zone planets are going to be facing very different radiative challenges to their habitability than those around G-type stars like our Sun. I'm not just talking about flaring events and heightened activity, but also M-dwarf stars will go through a prolonged pre-main sequence phase, and this can drive significant atmospheric escape even on what will be present-day habitable zone planets. And so what you're seeing demonstrated by this GIF for Proxima Centauri and the Sun is how the habitable zone is going to sweep in over time as those stars settle onto the main sequence. And for a fairly long period of time, Proxima Centauri is actually spending a lot of that early system evolution interior to the habitable zone, where it's going to be subjected to significant radiation. And so during this pre-main sequence process, we think most of the planets around an M-dwarf star of this nature are going to be experiencing pretty intense thermal atmospheric escape, especially for as long as they have water available on their surface or in their atmosphere. And the type of atmospheric escape we think is happening is pretty much demonstrated by this very small flow chart I've put up on the screen. So we like to first start assuming it is in what's called energy-limited escape. And so in this scenario, all of the incident radiation is either going into breaking apart your water molecules or driving the escape of hydrogen off of the top of your atmosphere. At this time, escape can also be so energetic that the flow of hydrogen will also drag heavier species away with it. And in our case, of course, we're interested in oxygen, which is the primary product of water photolysis being left behind. At some point, that oxygen is going to build up to such a level that it's going to throttle the escape of hydrogen, at which time we say the escape regime has transitioned into a diffusion-limited type of escape, where instead of being driven by the amount of energy coming in to photolyze or drive the escape of hydrogen, escape is rather limited by how quickly hydrogen can diffuse upwards through a static background of oxygen or heavier gases to reach the exobase, where it can then leave the planetary atmosphere. So this process can be quite energetic, and it can result in the permanent loss of oceans worth of water on these planets, depending on how long they're spending in this process. And so anytime you're interested in observing M-dwarf planets or interpreting their atmospheres, you really need to consider how this process has potentially shaped their evolution over time. And of course, one of our most beloved systems is the TRAPPIST-1 system, which I think is just evidenced by the sheer number of JWST proposals that have been accepted with some TRAPPIST observation that I'm showing up there on your screen. Let's see if I can get rid of this. Okay, there we go. And so several studies in the past have explored system evolution for single or tens of stellar evolution cases, and I'm talking about the escape evolution, of course, in this case. One of the examples is shown here from Lenkowsky et al. 2018. And what I mean by a stellar evolution case is, in order to get a result like this, where you have water lost over time and oxygen building up over time, you have to make some decision about how you're going to parameterize the stellar XUV environment and how that environment is going to evolve over time. But the thing is, uncertainty in our understanding of the XUV environment means that lots of different stellar evolutions through your forward model could be possible. And so these are constraints on various parameters of interest, such as the XUV to bolometric ratio, or luminosity ratio, the saturation time, the age of the star. And these are from Berkey et al. 2021. And so in our work, we employed this novel statistical approach to explore the full distributions on the physical input parameters of the TRAPPIST-1 system to determine uncertainty on escape outcomes. What I mean by that is we have uncertainty in the planet's masses, radius, eccentricities, and orbital periods. We also have this uncertainty on the stellar parameters that we're interested in. And we are taking an approach where we're combining all of these uncertainties to sort of translate them into our uncertainty on just how much water they could lose over time. And I will just note at this point that the results I'm going to show you are absolutely upper limits on the amount of water loss and oxygen buildup you might get through this process. I'll also note that we're not modeling surface oxygen sinks. And so instead of thinking of it as this is the oxygen that's built up in the atmosphere, I would encourage you to think more of it as this is the oxygen produced through this process that is then available for other planetary processes. So here are those distributions. On the top row, we're seeing the water lost as a function of initial water content in terrestrial or Earth oceans. And on the bottom row, we're seeing the oxygen produced also as a function of initial water content. The oxygen produced here is in bars, which, again, just to know, is dependent on the planet itself and its gravity. And so in the left column, we're seeing the interior planets, TRAPPIST-1b, C, and D. These never enter the habitable zone, and so we assume they'll be subject to this escape process for as long as they have water to lose. And then in the right column, we're seeing the outer planets, E through H. And the assumption we're making here is that once they enter the habitable zone, the incident radiation has decreased sufficiently that they will no longer be in this form of escape. And so that's where our study ends, at least, when they enter the habitable zone. So there's a few things to point out. Number one, the interior planets are becoming desiccated to a very high degree of certainty for all of the initial water contents shown here. And as it turns out, initial water contents up to about 50 to 100 terrestrial oceans. So what this means is the amount of oxygen that they're producing through this process is very tightly correlated with their initial water content. This is helpful because if you get a measure on oxygen with our model, it would be much easier to relate that back to an initial water content than it would be for, say, the outer planets. So let's talk about their behavior. What you're seeing is a little bit different to the interior planets. They have this flattening off of their curves, which is just indicating that they're reaching maximum possible values of water loss and oxygen buildup through this escape process before they enter the habitable zone. And I think a really big takeaway here is that the outer planets never lose more than 10 terrestrial oceans in our model before they enter the habitable zone. So this gives you a good sort of limit if you can try to constrain initial water content that might suggest that they are more or less likely to have retained water when they could have become habitable. And so around the time we had finished creating this initial parameter suite, the first JWST observations of the system were being published. And so the first one comes on TRAPPIST-1b. A 15-micron emission measurement was published by Green et al. 2023. I'm sure you're all familiar with this. But just to make sure we're all on the same page, what they found was that the 15-micron measurement matched up very well to what they would expect the equilibrium day-side temperature to be for an airless planet with no heat redistribution. So what you're seeing here, sort of on the bottom, those curves are more like atmospheres you might expect in the system. And then the two curves at the top show black bodies, where the green one is showing you the expected equilibrium day-side temperature. And so by eye, it's pretty easy to just pick out that their measurement matches up really well with what we'd expect for an airless planet. I will just put the caveat there that you should never draw conclusions from one data point. And there have been subsequent observations of TRAPPIST-1b that are a little bit more ambiguous than this. But let's just say for now, the simplest explanation is that it's an airless planet, and we'll work off of that assumption just for now. So after this measurement was published, a very similar observation was taken of TRAPPIST-1c by Ziba et al. 2023. And in comparison to TRAPPIST-1b, this one had a much more ambiguous interpretation. So this 15-micron measurement was about a difference of 1.7 sigma away from what we would expect an airless planet with no heat redistribution to have. So this left a lot more room for atmospheric interpretation. And one of the studies that did a really good job of this was Lankowski et al. 2023. And they found that this 15-micron TRAPPIST-1c measurement was consistent to less than 1.8 sigma with some of those bare rock surface models, and also oxygen-dominated and steam-dominated atmospheres. So in the context of the work I was just sharing with you, this is a really important result because an oxygen-dominated or steam-dominated atmosphere is exactly what we would expect for a planet that has undergone this escape process or is currently going through it. And so these are consistent with past or ongoing water loss. Just to drive this point home, here's a few more atmospheres that Andrew tested that were oxygen-dominated, but not shown in the paper, I don't believe. Or maybe they were, but not in the plot I just showed. And I think what's really interesting about this is some of these very realistic atmospheres, like the 0.1 bar oxygen with portions of CO2 or portions of water, are consistent to the measurement in under 1 sigma. And one thing that I found really interesting was that the pure O2 1 bar was consistent to 0.01 sigma, so very, very close, although of course the pure oxygen atmosphere is maybe not as realistic as one with some CO2 or water. But anyways, let's work in the realm for a minute that TRAPPIST-1b is airless, while TRAPPIST-1c could potentially have a past or ongoing water loss atmosphere, so something with current oxygen in it. So I want you to recall this plot that I showed that gives the oxygen produced as a function of initial water content. And I'll note now that TRAPPIST-1c always builds up the most oxygen in our model. This is because it is larger than TRAPPIST-1d, so it has better gravity, but it's also further away from the star than TRAPPIST-1b, so it's not subjected to quite as much radiation. And so what that means is that for the same initial conditions and geochemical properties, what I'm saying is for very similar oxygen sinks on the surface, there would be a narrow range of initial water content that would result in no atmosphere on TRAPPIST-1b and some current oxygen on TRAPPIST-1c. And so this is the logic we follow to try and get to a potential lower limit constraint on initial water content of the system. And I'll note here that we are going to underestimate oxygen sinks that you might expect, and the point of that is to get a conservative lower limit, because as oxygen sinks increase, you would need more and more initial water content to produce extant O2 on TRAPPIST-1c today. So here's the 3 additional oxygen removal processes we add in. These are all fairly standard and have pretty good numbers in the literature that I've listed here. And when you apply these oxygen sinks to the result that I just showed you, this is what you're left with here on the left. So we're seeing the oxygen left now after the escape process and this additional removal as a function of water lost, which is synonymous with initial water content in this case because these planets are becoming completely desiccated. And immediately by eye, I'm guessing you should be able to pick out the spot where you might expect TRAPPIST-1c to be more likely to retain oxygen, while TRAPPIST-1b remains airless. And we take this a step further by running a Markov chain Monte Carlo simulation to find the initial water content that results in a 0.1 bar oxygen atmosphere on TRAPPIST-1c and complete atmospheric loss on TRAPPIST-1b. And these are the results of that Markov chain. And so it's pretty good validation. It matches up with what you would expect just by looking at the distributions. And it's reporting that it would expect an initial water content of at least 8 terrestrial oceans for this atmospheric scenario. And so, as you might expect outer planets in a planetary system to form with comparable or greater initial water content than the interior planets, we apply this initial water content to the outer planets in our model, we would find that they would all retain greater than 1.7 terrestrial oceans at habitable zone entrance. And so following this chain of logic, it would be very useful to confirm or deny the presence of oxygen in TRAPPIST-1c's atmosphere, because it might be able to inform us on the relative likelihood that the outer planets still had water when they entered the habitable zone. So all of this work that I've just shared with you, including many other analyses and all of the caveats about our assumptions, are in a paper that I just published back in June. So I'd encourage you to go look at that if you're interested in this. But at this time, I'm going to switch gears a little bit to start talking about habitable worlds, observatory, and stray light considerations. So how did I go from studying TRAPPIST-1 atmospheres to doing basically optical engineering? Good question. I'm glad you asked. I actually spent this summer between Redondo Beach with Dr. John Ehrenberg at Northrop Grumman and Goddard Space Flight Center researching these stray light constraints. And this is a part of the University of Washington's research rotation. So in order to get my PhD, I have to do a full quarter working in an area of research that is not my specialty. And aerospace engineering is certainly not my specialty. Maybe it is now, maybe not. We'll see. But what I elected to do was some of this precursor work for HWO. So I want to frame this stray light problem for you for a minute, because as we see with JWST, stray light is not the limiting background. It's really thermal noise. And so stray light is recently, I guess, making a comeback as something that people should be concerned about. So let's recall the goals of HWO for a minute that were outlined by the decadal. And I like to think of them as sort of split up into 2 particular charges. One of them, at least, is to survey at least 100 nearby stars and search for Earth-like planets in at least a quarter of those systems. And the other goal that HWO was directly charged with was to characterize the atmospheres of at least 25 of our most promising Earth-like exoplanet targets. And so this is sort of how I imagine the mission going, because exoplanet science is obviously the only field of science that matters. It's going to be contained in the mission lifetime. But even if we take that to be true, doing this is really easy to say, but it's very, very difficult to do in practice. It's going to take quite a lot of observations, a lot of revisits to the same system to actually do the detection process, and then even more to do the characterization process. And one other big challenge with this is that if you want to constrain the orbital parameters of planets that you're detecting, you really need to be able to go back and point at very specific systems at very specific times. And so you don't have as much freedom with constraining or pointing directions of the telescope. What that means is if you want to maximize your science, very likely you will eventually be pointing in a direction that is not so favorable in terms of micrometeoroid damage. So micrometeoroid damage is something that we see affecting JWST a lot more, I think, than what was expected. And I just want to talk to you about how micrometeoroid damage can contribute stray light over the mission lifetime. So let's imagine you have a primary mirror, secondary mirror. You're looking at your field of view, which is the orange star, and then you have, of course, the rest of the sky all around you, so lots of other astrophysical background sources. In a perfect world, you would imagine your mirror would perfectly specularly reflect all of the light you're interested in up into your secondary mirror, into your detector, and everybody would be happy, and it wouldn't reflect the light from the other background sources into your image plane. Well, now let's imagine that you have some micrometeoroid hit. Spent a long time on that animation, by the way. So now, all of a sudden, there's going to be portions of your mirror that are no longer, quote unquote, perfect. They won't even be perfect to begin with, but let's imagine they were. All of a sudden, you're going to have these damaged areas now scattering stray light into your observation. And so if you go up there with your telescope and you have no plans for either preventing or mitigating this, this represents an irreversible addition of stray light to your observations over the mission lifetime. And here's just an example. This is wavefront error, so it's not really the same thing as stray light, but I think it demonstrates well how these micrometeoroid hits can start to impact your primary mirror on JWST, at least. And so in this work, since we are so early in the mission design process for HWO, now is the time to figure out if this problem is something we should be concerned about. And so one thing you can do is slap a barrel onto your telescope, and that can help you to not only prevent stray light from actually reaching any damaged parts of the mirror, it can also help you to reduce the rate of micrometeoroid damage, which is why you'll probably see in all of the EICs, they have barrels on them. This is one of the reasons why that might be favorable. And so considering a telescope with a barrel of different designs, we're interested in providing reliable order of magnitude calculations for the stray light habitable worlds will experience as a function of defective mirror area. This will allow us to better assess the threat of stray light this early in the mission design process when we can really do something about it. And in addition to this, we're trying to connect this potential stray light buildup over time to science requirements such as yield calculations. So in the most simplest scenario, how can we assess stray light? Well, I would argue that the simplest thing you can think of is, let's imagine you only have the host star as a potential source of stray light, and we have a point source surface mirror. So in this first case, all of the light from your host star is going to come in at an incidence angle of 0, hit your primary mirror, and be reflected back up at a reflection angle of 0. And then what we're really interested in is the amount that gets reflected into the angular size of the planet's point spread function. So in this case, we're imagining that all the stray light that gets reflected back up into the secondary mirror is diffuse and spread out equally. And so you're just interested in the fraction that makes it into the planet's PSF here. So I promise I won't put a lot of equations up on the screen, but we are going to have to look at one so you can understand the results here. And so the light received from the planet of interest in our first case, we're saying must be greater than the stray light from the host star that is scattered by defective mirror area A sub D. And so this light received from the planet of interest, that could be any stray light requirement that you want. Maybe it's 3 exozodis worth of brightness. But for now, we imagine that a fairly okay requirement to start with is that you want the planet to be brighter than the stray light. Sure. So that is going to look something like this when you write it out. So on the left side of the inequality, we have the flux of the planet times the area of the primary mirror, so all the light you're getting from the planet. And then on the right side of the inequality, we have the flux of the host star times the diffective mirror area times this disgusting-looking integral. And I can make it look a lot simpler by doing this. All that term is what's called the bireflectance distribution function, or the BRDF. And the BRDF, to first order, is just in charge of defining the scattering properties of the damaged mirror area. So on the left, what we're assuming is that the mirror is perfect, basically, and it's reflecting all of that light perfectly, but damaged mirror area is not going to be perfect. And so we have this function that kind of tells you what fraction of light you expect to get reflected into a particular solid angle. And so then we can sort of rearrange this equation to get to something which gives you the fraction of allowed defective mirror area before your particular stray light requirement is violated. And so when I talk about the maximum allowed defective mirror area, the maximum fraction of defective mirror area, this is what I am talking about in the remainder of the talk. So in general, surfaces have 2 primary types of reflectance. You can either have diffuse reflectance, which is like a Lambertian, or you can have specular reflectance, which can be represented by a Dirac delta function. So on the y-axis in both of these plots, we have the value of the BRDF at a given scattering angle, assuming the light is coming in at an angle of 0 degrees of incidence. And so diffuse reflectance is basically just saying light is being equally probable to scatter in all directions, whereas specular reflection is saying all of the light is going to be perfectly reflected back into your angle of reflection. In reality, all surfaces, I mean, rarely are you going to see something that's like so perfect in one way or the other. So most surfaces are going to be some combination of these two. And so one illustration I like to show of this is the Phong reflectance model, which is just a very simpler diffuse component and a specular component. It's governed by a few of these different parameters, which are not super important, so don't worry about them too much. Basically, this n value is telling you how sharp this peak is, and the rho sub d is the diffusive reflectance, rho sub s is the specular reflectance. So you can see based on how you tune these parameters, it's changing how that BRDF is going to look and how light is going to be reflected back into your angle of reflection. And so for the different types of defective mirror area we're considering, they all have slightly different BRDFs that you would want to use. So here are the 3 primary categories we're interested in: mirror roughness or optical coating roughness, micrometeoroid damage, which is the big one, of course, and finally contamination, aka dust or stuff that gets onto your mirror. So starting with mirror roughness, the industry standard is really what's called the Harvey-Shack BRDF model, or the ABG model, but I'll be showing you Harvey-Shack. And this is primarily looking at some surface, and it's interested in this roughness that you're seeing here. So again, no surfaces are perfect, and as best as we can polish these mirrors, we're going to do so, but there's still going to be some of this nonsense going on. And so the Harvey-Shack model is primarily looking at how big this these bumps are, which are going to be like very small, microscopic maybe. A very common, say, value of this roughness for mirrors, for example, is about 13 angstroms and root mean squared value. And so the Harvey-Shack model looks like this. And so what I'm showing you here is, again, this BRDF as a function of reflectance angle for various different incidence angles. So what you can see is that Harvey-Shack is very specular in nature. Most of the light is being reflected into the same angle of reflection that it is getting in incidence. An interesting thing that you're already seeing in Harvey-Shack, and you'll see in a lot of the other models, is that as you start to get to very large angles of incidence where it's grazing the mirror, light is actually being reflected more predominantly, again, into that specular reflection, which is interesting. But in general, I'll note that this y-axis is linear scaled, which does not mean that it is actually very specular reflecting. And in our host star only case, if we said that our entire stray light budget was going to be allocated to mirror roughness, you would be able to tolerate something up to about 190 angstroms, which is like huge. That would be not a problem at all. Of course, our straight light budget is not fully allocated to mirror roughness. We have two other types of defective mirror area, which are much more difficult. I'm going to skip over micrometeoroid damage for a second and talk about contamination or dust. The industry standard for this is really Mie scattering of particles on a reflective surface. So I'm sure a lot of astronomers here are familiar with Mie scattering. Now just imagine you have your dust particles and we slap them on top of a mirror. So that's what's happening here, and as it turns out, Mie scattering is very, very complicated. I'm sure I don't need to go into detail on that. And so instead of doing it with like an analytical function, which is how we're handling the other types of defective mirror area, we're taking a slightly different approach. And so Bob Podgorski sent us these BRDF curves with Fred, which is a software used to do ray tracing in a lot of straight light calculations, especially here at Goddard. And basically what we have here is different BRDFs for different incidence angles. You can see Mie scattering, similarly to the Harvey-Shack model, is primarily specular. It's even more so if you note that the y-axis is in log scaling. And our goal here is eventually to be able to interpolate between these curves to get back to any angle of incidence and then numerically integrate the area under the curve using Python. But that is still a work in progress. It's difficult. And what I'm not showing you in this plot is the azimuthal angle dependence. This is just sort of the angle from the surface normal. So I will have to get back to you on the results of this. But moving on to micrometeoroid damage, a common method for this is using what's called the Peterson model for digs. So this model was used to simulate micrometeoroid damage in several different projects, including the LISA mission a few years ago. And so the Peterson model for digs is primarily looking at something that you might think of like this on a mirror, so it's a scratch or a dig. And what we're doing for micrometeoroid hits is treating them as if they're perfect spherical craters on the surface and calling them a dig. The thing is, in order to get the crater size caused by a micrometeoroid hit, you also have to relate the impactor mass to crater diameter, and this turns out to be less than an exact process. So here's a ton of different models that we've considered that relate these two parameters. And I will note that the y-axis, which is basically telling you that crater area is in log scaling. And so these models are spanning multiple orders of magnitude in their predictions. For now, I'm going to just pick out a sort of optimistic case and a pessimistic case to talk about, where the optimistic case would tell you that you can have more damage and be okay. The pessimistic case telling you you need to have less damage. And so that would be the Watts and the McHugh and Richardson, or MR models. And again, these are very, very specular. So you can see, again, y-axis is in log scaling. And so these peaks are quite sharp. And they look very similar. The only difference really is that the MR model predicts that you would have much more reflection in a given direction than the Watts model. And just for reference, these plots are just picking out one specific impactor mass to show you what the BRDFs would look like. So one of the initial results that we have for this is relating the maximum allowed damage area to a given impactor mass. So assuming all of your hits were due to one impactor mass and saying you have one impact per meter squared on your mirror, you can get curves that look like this, going from 10 to the negative 18 grams, which is very, very tiny, all the way to a gram of a micrometeoroid impact. And you can see that the allowed damage fraction ranges from, 1 billion times the area of the primary mirror, not a problem, all the way down to 10 to the negative 19 times the primary mirror, which is much scarier, if you ask me. So you wouldn't really be able to tolerate even one hit in that case. And so where we're heading with this is to actually look at what we might expect the distribution of impactor masses to be over a given time period for the telescope. But up until this point, even now, I'm still talking about this host star only case, where we have this point source mirror, all the stray light is coming in from the host star. In reality, of course, space is not that simple, neither are telescopes. And so there are, unfortunately, many, many more sources of stray light than just the host star. They're going to be all around your observation. And in addition to that, the mirror is not a point source. You have a spatially resolved primary mirror, some barrel that's going to be blocking a lot of those optical paths. And because of the BRDF's very strong dependence on all of these angles of incidence and reflection, you really need to treat the mirror as if it is, in fact, spatially resolved when you're trying to model more than just the host star. And so we have developed a stray light model to do this in this sort of order of magnitude estimation approach. And I'm just going to bring up this equation one more time, and I promise we'll never look at it again. So here's the first equation we have, and you can change that back into what we know as the full description of the BRDF. And then if you want to scale this up to be for any source of stray light on the sky at any given reflectance angle, incidence angle for a spatially resolved primary mirror, so NS number of sky points, NDA number of mirror points, your equation is going to turn into something that looks like this, which is much uglier, but we can just break it down really simply into your stray light flux requirement divided by the sum of all flux contributions from every sky point onto every mirror point. So that is how we're getting to this damage fraction again. And we model our observations onto compiled maps of Gaia data. I was very pleased with this because I do a lot of atmospheric characterization, which are squiggly lines on a plot. Rarely do I get to make something that actually looks nice to look at, so that was satisfying. And what you're seeing here are compiled maps of Gaia data where the sky is broken down into degree by degree boxes. And we found the cumulative flux in each box in the Gaia G band, the Johnson V band, and the Cousins IC band. And then in the upper right, I'm just showing you just the sheer number of sources in each box, which is also a good check to see that the galactic bulge has the most sources. So when we model observations onto one of these maps, it starts with initializing a telescope model. So we can handle any sort of barrel geometry with any amount of scarcedness. And we can also rotate our telescope relative to the sky plane, which is important if you have an asymmetric barrel to be looking at. After the telescope model is initialized, the stray light model decides what sky points can see at which mirror point. So this is just a representation of that, where it's telling you the fraction of the primary mirror that each sky point can access that has an optical path that is not blocked by the barrel. And then the model uses that to determine what portion of the sky is actually going to be affecting your observation. And then in the guts of the code, of course, it's going in and actually doing the calculation for each sky mirror point pair that's relevant. So I have one other result to show you today. We're still kind of in the process of doing a lot of these results for this spatially resolved sky and spatially resolved mirror. But here's one interesting thing, which I think reinforces an idea that we're already pretty comfortable with, which is that observation prioritization should perhaps be given to high luminosity targets and those close to the galactic plane. In other words, it's going to be more difficult to observe targets that have more strict contrast requirements and those that are closer to the galactic plane. And so what I'm showing you here is, again, just for a fiducial Peterson model, so assuming the impactor mass is 10 to the negative 10 grams again. On the left, we're seeing that host star only case. And so it's what you'd expect. It looks pretty uniform just as a function of host star luminosity, aka the contrast with its Earth-like planet. And then on the right, I'm showing you the allowed damage if you consider all of the stray light sources in your target's pointing box. So if you think back to these maps of the sky, what I'm calling the pointing box is whatever degree by degree box your target is contained in. The closer you are to the galactic plane, the more sources of stray light you're going to have very close to your field of view. And so it's a good sanity check because it is what we would expect. You can see a lot of these stars that are close to 0 degrees latitude all of a sudden get way, way more sensitive to the amount of damage you have on your primary mirror. One thing that I think is important to keep in mind here, though, is that this is just for if we assume our stray light requirement is the planet host star contrast. So if you were to switch the stray light requirement, say, to a few exozodi, this is going to look a lot more optimistic. And that is another result that we are working on putting into the paper, but I don't have an exact slide on that today. So I did just want to mention, it's a good segue, into the analyses we currently have in progress, which will be put into the paper and hopefully submitted later this year. I said it, now we have to do it. So the first one is how do different barrel geometries improve your rates of micrometeorite impact as well as cumulative stray light flux in an observation? I realize this is misleading. When I say improve, I mean reduce. So we are going to be taking a few different barrel geometries informed by the EIC designs and plugging them into the model and seeing how their levels of stray light differ. What you should see is that the longer the barrel is, the more favorable the stray light is, as well as the micrometeorite damage will go down too. we're going to look at optimal barrel rotation. So once again, the model for a scarfed barrel can handle rotating it with respect to your target. And we'd like to see if that rotation can actually get you a significant improvement on stray light, or if it's not really worth worrying about. And then finally, and I'm most excited for this one, we're going to connect this micrometeoroid damage and the other forms of defective mirror area that I talked about and stray light to Habitable Worlds Observatory yield calculations with Chris's altruistic yield optimization calculator. So the idea here is that AYO will basically take a telescope design and tell you, estimate your yield calculations based on completeness of systems. I think I said that right. Okay. And what we're going to do is basically say, okay, at ground level, there's no stray light. Here's what your yield calculation might be. And then we'll use the stray light model to say maybe 5 years into the mission, maybe 10 years into the mission, here's the stray light we would expect for our list of targets. And then we're going to pass those to AYO and see how AYO then handles more noise in its observations and how that affects the yield numbers. So with that, I'd like to leave you guys off with a few conclusions. First one is stray light due to mirror damage may jeopardize the goals of HWO, and mitigation and observation strategies, I mean science policy, precursor surveys, and habitable worlds technology development should be considered early in the mission design process. So I think stray light due to this form of damage and defective mirror area is going to have a much larger impact on HWO than many of the space missions that have come before it. It's really something that we need to keep in mind as we're moving into these early phases. And we've got to kick it back to TRAPPIST-1 for a minute. Observing the TRAPPIST-1 interior planet's oxygen abundances will likely allow us to better constrain initial water of the system. If TRAPPIST-1b has no atmosphere, while TRAPPIST-1c has any tenuous oxygen in its atmosphere, our models would predict a lower limit of initial water content of about 8 terrestrial oceans. And I'll actually note that this prediction for initial water content was in agreement with what was published in Ziva et al. 2023, who analyzed initial water content from the perspective of carbon dioxide abundances. And then finally, with an initial water content of 8 terrestrial oceans, the outer planets would all retain greater than 1.7 terrestrial oceans at habitable zone entrance in our model. So I would argue that observing the interior planets with JWST would be very valuable to our understanding of also the outer planets in the system. Can you guys guess what I'm interested in doing with JWST? So with that, I just wanted to say, thank you to the University of Washington's astrobiology program for bringing me here to Goddard on the research rotation. Say thank you to Chris Stark for advising me for free, and to John Ehrenberg for doing the same, and Dr. Aki Roberge. And thank you guys for coming to
Awesome. Thank you so much, Megan. That was a great talk, and thanks for dealing with the tech issues at the start.
My pleasure.
So yeah, we have plenty of time for questions. So folks in the room can raise your hand, or you can also raise your hand online or post it in chat, but here we go.
Excellent talk. So impressive. Your presentation is just awesome.
I really appreciate that.
Making our exposure to this material all come alive. Thank you.
Thank you so much.
My question is whether we know anything about the magnetic field of these planets, TRAPPIST-1 system, whether it's global magnetosphere or localized magnetic field structure.
Yeah, that's a really good question. I would love to know the answer to that. Unfortunately, I don't quite know the answer to that. If I had to guess, I would say that, a lot of the TRAPPIST planets are very small. Not B and C, but, D, E, H. They're very, very small. And so I would expect that they would have weak magnetic fields. That's purely based off of my basic understanding of magnetics and physics when it comes to planets. So I would definitely want to look more into that, too.
So do you expect them to impact the kind of rate that you calculate?
Oh, the escape rate.
Yeah.
This is an interesting question. When it comes to thermal escape, not as much, but once you get to non-thermal escape mechanisms, absolutely, it should impact them. And I would even expect, and there's been work done on this by, say, Dong 2018, for those outer planets, once they enter the habitable zone and they're kind of safe from this very egregious form of thermal atmospheric escape, some of those non-thermal mechanisms are more likely to take a dominant role in how their atmospheres evolve over time. And so I would think that the magnetic fields would be something important to that.
Great. Thank you so much.
My pleasure.
Great. I think we'll go online. Richard, do you want to come off mute?
Hi, and thanks for this great talk. Really enjoyed it. I wanted to ask, all right, so one of the kind of future missions that we're thinking about is an interferometric version of habitable worlds, or I guess a terrestrial planet finder interferometer type thing. Do you think I wondered if that might be any more robust against this sort of diminishment of capability due to micrometeoroids? Do you have any sense of that yet, or has anybody studied that?
That's a good question. In this work, we were primarily looking at like a single telescope design. With that being said, if you want me to wax poetic on what I might expect to happen, I would think that in some ways it could be more robust, of course, because you have multiple different telescopes that are kind of working together to conduct an interferometry, or multiple different mirrors. And I would imagine as far as servicing is concerned, it would be easier to replace a small primary mirror than a very large primary mirror. So I guess my very naive estimate of what might happen is that it would be maybe a little bit more robust in that way. But at the same time, if you get damage to those components of the interferometer, I would still expect that to be contributing stray light in a very similar fashion.
Cool, thanks.
Hi, Vincent Kaufman. Very nice talk. Very impressed with the diversity of work you're working.
Thank you.
So what really scares me is that the way I understand it, that the coronagraph relies on sort of a spatial separation between the host star and the planet in order to filter the stellar light, right? What if there is a spatial component of stray light that is translated into the coronagraph? Will that provide a big problem for filtering out the host star's light?
Truthfully, this is probably a better question for Chris, who's a lot more familiar with coronagraph technology.
So that's kind of what this is that you're tracking the fraction of the stray light that ends up coincident with the planet. Okay. But related to what you're saying, it's a great question, because one of the things that we were just discussing the other day that we're concerned about is this all assumes that you can model the stray light and subtract it from the observation, and it just contributes shot noise to your exposure time equation. If in reality the stray light is this weird pendulous thing, which we have seen with JWST, then that might not be the case. But generally, I think it's true that those sorts of stray light features are caused more by like internal instrument reflections and stuff that's way more complicated than what we're modeling.
Yeah. I think we're definitely taking, or at least trying to take an almost optimistic approach to how we'll be able to handle the stray light. But the other person working on our project, John Ehrenberg at Northrop, said if he had to tag this work, he would say the tag would be afraid. Be very afraid. I think that's funny.
Yeah, so I have a kind of similar question in making this really complicated. Is you showed that you found that the stray light is very dependent on your angle, your incident angle. And the whole idea behind the barrel is that you're trying to reduce the number of angles, if I'm understanding correctly. And you're talking about the micrometeor impact on the mirror, but what if we are getting impacts on the barrel itself that's causing leakage, stray light? Because I assume it's a much bigger surface area, so much higher probability of impacts on the barrel itself. So I'm just curious if you had any.
That's a really good question, and that is something that I would highly encourage NASA to be considering as they're trying to design their barrel. So in this work, we are assuming the barrel is like perfect, and anything that hits it not getting through. In reality, that's not necessarily the case, as you said. So one thing you might be able to do is put a lot of layers to prevent something from getting inside. But I think one thing that's almost scarier than that is, let's say you have a micrometeoroid come into the barrel, hit the side of the barrel as opposed to the mirror. In our work, we imagine that micrometeoroid gets absorbed by the barrel and it's gone. Nobody has to worry about it. In reality, it's probably going to split apart into lots of dust, and it's going to increase the contamination, aka me scattering, on your mirror over time.
Yeah.
And so two things you might want to consider with this mission would be, can we mitigate micrometeoroid damage after they hit? But in addition to that, can we clean the mirror when it's already in orbit?
Great. Any other questions in the room or online? Any? Well, another question going back to your first project you talked about, and because we talked about very briefly that I'm interested in outgassing and atmospheric escape and everything like that. So what you briefly showed, I think some of Josh's work talking about the absorption back into the crust as a loss mechanism. Yeah, and I was just curious what just more details on that. Like, what are you using in those models?
Yeah. Okay. So. Sorry, this is so far back.
Oh no, it's okay. Sorry.
There you go. Okay.
Yeah.
So when it came to putting oxygen removal processes onto this, I wanted to be very careful because we are looking at a lower limit. So I didn't want to, say, arbitrarily put that at a very high initial water content. So to me, when it comes to oxygen removal by the surface, magma ocean, especially if you're in hydrodynamic thermal escape, seems like it's going to be a pretty big sink. That's why I added it. Dry crustal oxidation, that comes from Josh KT's 2021 work. He did a very similar study to what we are actually doing with this. And if you look at my paper, I actually have an entire results section where I directly compare Josh and my results over time. And they match up very, very favorably, which is why I felt comfortable adopting his oxygen loss process. And then the non-thermal escape adjustment of 100 bars total, Josh did this as well in 2022. But based on the work I've seen on non-thermal escape of the TRAPPIST-1 planets, this is probably quite the underestimate, I would be honest. So that's why we're taking this conservative approach. But with that being said, when it comes to those outgassing processes and surface-atmosphere exchange, as it just so happens, this is what I'm interested in for my next project of my dissertation. Awesome. And so I'll be trying to actually model in a photochemical model self-consistent atmospheres that have outgassing at the bottom and realistic escape rates at the top. So if it's something you're interested in,
yeah, we should talk. We should talk. Awesome.
Yeah.
Great. Yeah, Avi.
Great talk. You point out that 0.1 bars is the kind of best scenario for an atmosphere, but that there are many non-atmosphere free solutions from Andrew's work. How stable would a 0.1 bar O2 atmosphere be to all the loss processes over long periods? And would that suggest that that solution is kind of either very temporary or not actually the most likely one?
Yeah.
What do you think about that?
It's so fun that you asked that, actually, because that is one of the questions we're hoping to answer in this next work, is using the VPL climate model and the photochemical model. We're going to try to see if we can actually get tenuous atmospheres like this to be stable over time. And the answer is outgassing, right? If you have a 0.1 bar atmosphere like this on TRAPPIST-1, more than likely you're going to lose it on the timescale of millions of years. But it is very, I wouldn't go as far as to say very likely, because I'm not sure yet, but I would not be surprised if there is outgassing going on these planets. Number one, they're experiencing an insane amount of tidal deformation, most likely. And number two, the fact that we are seeing such high escape rates when it comes to thermal escape could support that idea that outgassing is occurring if we are able to confirm that there is oxygen in the atmosphere, for example. And then Trent Thomas at University of Washington has been doing a lot of work to constrain the outgassing rates that you might expect on the TRAPPIST-1 planets. And so that's something that we'd actually like to do, is use that outgassing to see if you can stabilize the spin atmosphere. And if you can, and then you can observe something with JWST, that would provide you a lot of support that they are currently outgassing. With that being said, comparing to those bare rock surface models that you mentioned, yeah, that's absolutely a case that could be very likely still, for TRAPPIST-1C even. I would like to know the answer to that, of course, and we're working so hard on those JWST proposals, but I think the point of this result, and I tried to be very careful with how I framed it in the paper as well, the point I was trying to make was, in this scenario that is still consistent with observations, we can follow this train of logic, and therefore we should try and confirm whether or not it is the case with observations as well.
Great. All right, most important question. Pretend Chris is not in the room. What is better, optical engineering or the atmospheric research?
Well, considering UW has already hired me, and Chris has yet to hire me.
Wow, okay. Okay, you really went for it. You pretended he wasn't here. I love it. Awesome. Well, let's thank Megan again for the awesome talk, and best of luck as you finish up your dissertation.
Oh, no, no worries. Don't even worry about it.